Today I am going to discuss what is deadlock and what do you mean by system models. So let us start. Now see this situation. What you see on the screen is that there is one crossroad is there, isn't it? Now what is happening here is that two cars are there. Okay, these two cars cannot move ahead. Why? Because in this lane, these two cars are there and which are blocked by this set of cars. And again, these are two sets of cars that are actually blocking this cars. So this situation in which none of the cars are able to move ahead. This typical situation can be termed as deadlock. Now, I'll show you one diagram regarding this. See, this is a real life example. Many times maybe on Dwarka, you may have experienced this. See, what is happening here is that, see, this set of cars are there. This set of cars are there. And in any situation, this is a complete block, isn't it? Means nobody can cross the road in such a situation, isn't it? So how will you define deadlock in terms of operating system? That is what we are going to study today. Now this was some real life example. Now we will discuss this term deadlock in terms of our operating system. What happens in a system? For example, let us take one process, right? There are many processes in the system, we know that. So say suppose consider one process P1. Now maybe that at present moment it is holding one resource R1, right? Now resources could be anything. It could be scanner, it could be printer, it could be memory, it could be CPU, anything. So currently this resource R1 is being held by this process P1. Say suppose for completing its work, this process requires a resource called as R2. Now suppose simplicity, let us consider this R1 as CPU. This is one resource. Now for completion of a job, say suppose it requires resource R2. Say suppose you will consider this resource as scanner. So what is the situation? P1 is having CPU and it is requesting scanner. Now say suppose this particular scanner is being held by a process called as P2. So this scanner is being acquired or allocated to process P2. And say suppose if this particular process P2 for its completion of activity, say suppose it requires resource R1. So what is the situation here? P1 is holding a resource, it is requesting another resource. P2 is holding a resource and it wants another resource. But what is happening is that neither P1 will get both the resources and it will not complete its work. Neither P2 will get all the resources and will complete it work, right? So this is a situation which is blocked. Means both these processes P1 and P2 are both blocked because each is holding one resource and requesting another resource. So this situation is nothing but the deadlock. Now let us define where particularly this deadlock will happen and how to deal with that. Now say suppose mostly this deadlock will happen in the multi-programming system. Now it multi-programming system, what is happening is that multiple processes are there and they are competing or they want resources. So resources are finite. Finite means what? Limited number. So such type of block situation will occur in multi-programming system. In multi-programming system, there will be multiple processes, but they will require resources and resources are finite, isn't it? Finite means what? Limited. So in such situation, what will happen? Each process may hold one particular resource and it may request another resource, and that particular resource may be held by another process and it may be requiring another resource. So such type of cycle or block structure will happen, and this situation is nothing but the deadlock. Now let us define where particularly this deadlock will happen. So deadlock will exist among a set of processes if every process is waiting for an event. Means here in this particular diagram, what is happening is that this P1, it is waiting that this particular resource R2 will be released by this particular process P2. So here in this situation, P is waiting to get the resource R2, isn't it? Then this particular event can be caused only by another process in the set. Now in this situation, P1 is waiting for resource R2, which is being held by this particular process P2. And what is happening with P2? P2 is holding resource R2, but it is requesting a resource R1 being held by the process P1. So what is happening? P1 is waiting for this resource R2, and this waiting is not getting changed. Means P2 will not release this R2. Why? Because it is requesting R1. And P1, it will not release R1 because it wants R2 as a resource. So this waiting process of P1 and P2 is not getting changed. Hence we will say here there is a deadlock. So deadlock will occur if the process's state, that is waiting state, is not getting changed. Means P1 will continuously wait for resource R2 and P2 will continuously wait for resource R1. So this state is not getting changed, hence we will term it as deadlock. Now let us define it once more. So how will you define deadlock? Deadlock means what? It is a set of blocked processes. Here in this diagram, P1 and P2 are both blocked processes, each holding resource. In this situation, P1 is holding R1 and this P2 is holding resource R2. So both the processes are holding some resource. And what they are doing? Waiting to acquire resources held by another process in the set. Now this P1 is holding resource R1, isn't it? And it is waiting for the resource R2, which is being held by the process P2. P2, it is holding resource R2 and it is waiting for resource R1, which is being held by the process P1. So this is nothing but called as deadlock, right? So deadlock means what? The waiting state of both the processes P1 and P2 is not getting changed, means they are not moving ahead. System is blocked. We will term this situation as deadlock. Now we will consider what actually is a system model. So for that, first we have to understand this, that a particular system, it consists of resources, isn't it? Now resources could be anything and they will be represented by this R1, R2 till Rm. Means resources may include CPU, memory, IO devices, printer, scanner, whatever. All will be termed as the resource. Then each resource type Ri has many instances. Means there could be multiple instances of a particular resource. We say suppose now CPU will only be one, but say suppose printer, there may be two printers. Now regarding IO devices, maybe say suppose two scanners are there. So likewise, so there can be many instances of a particular resource. Now each process, it utilizes a resource as follows. So how a process is going to use a resource? First, it is going to request a resource. So say suppose whenever we want something from somebody, so first approach is that we request that person. that okay, you are having this particular thing. Like say suppose I am standing in a particular, say suppose bank, and I am not having a pen. So another person is having a pen. So what will be my first approach? I'll ask that person to give me the pen. So pen is a resource in this situation. So first thing the process does is that it requests a resource. Now, if a resource is available, access is granted. So in a system, suppose a particular resource is there. Like say suppose I am requesting a scanner or a printer. So if that particular resource is available, then access is granted. Means I will be given that particular resource. And if that resource is not available, then the process is blocked. Blocked means what? Then the process will go to the waiting state. If a process requests a resource, if it is available, then it would be given the resource. If it is not available, then the process is blocked. Blocked means what? It will go into the waiting state. Now after request, suppose it gets that particular resource, then what it will going to do? It will use that particular resource, isn't it? Suppose the process requested a scanner and it got its access, then it will use the particular resource. And after using it, what the process will do? It will release that particular resource. Why? Because other processes will require that particular resource. So after my usage, I have to release a particular resource. Now in this situation, what will be the undesirable scenario? Undesirable scenario will be like I have shown you in the earlier diagram. Suppose process P1 acquires resource R1 and is waiting for the resource R2, isn't it? And process P2 acquires resource R2 and it is waiting for the resource R1. So what will happen in this situation? Both the processes will go on waiting for the particular resources, and both the processes will be blocked. Their waiting state will never change, and this situation will lead to deadlock. And this is the undesirable scenario in this situation. So what is deadlock? Deadlock is nothing but it is a set of block processes where one particular process may wait for another particular process where it is holding some resources. Now we will see how actually these processes and resources are represented graphically. So we are going to study a graph which is known as resource allocation. Now in data structure you have studied what is graph. Graph is nothing but it is a set of vertices and edges, isn't it? So here also how the different processes and resources will be represented. So let us see. As I have told you, graph is nothing but it is a set of vertices known as V and a set of edges called as E, isn't it? Now in this situation, our vertices are partitioned into two types. So in our system, we are having process and the resource. So process will be represented by this oval structure like I have shown you in the earlier slide. And the resources will be shown by the rectangle like I have shown you in the earlier slide. This vertices, as I have told you, it is partitioned into processes which could consist of set P1, P2 to Pn, and the resources will consist of set of resources which may be represented by R1, R2 to Rn. Now after vertices, next we are going to see edges. Like these types of arrows we have drawn, isn't it? So these are nothing but the edges. So there are two types of edges. One is known as request edge, which is directed from process to Rj. Means say suppose this is particular process P1 and say suppose it wants a process called as R2, isn't it? So this is known as the request stage. Now say suppose this particular process is having a particular resource. So that will be known as the assignment age. So this is known as the assignment age and this is known as the request age. So it is a very simple graph. This graph consists of two sets. One is known as vertices set, another is known as edges. The vertices will consist of process and resources. Process is represented by oval structure and resource is represented by rectangular box. And there are two types of edges. When a process is requesting a resource, it is known as request stage. And when a particular resource is being held by the process, it is known as the assignment age. So here, as I have explained in the last slide, process represented by oval structure. Now, resource, as I have told you, it is represented by rectangle. So suppose this resource is having 4 instances. Means say suppose my pen is one resource and if I have 4 pens, then means I have 4 instances of pen. It's like that. So resources here, suppose 4 instances are there. So it will be represented by this 4 rectangles within that larger rectangle. And say suppose when PI requests the instance of RJ, it will be redirected like this. Okay, this is known as the request age. And when the particular process is holding an instance of resource, then from this inner rectangle, one arrow will be drawn towards that particular process. So this is known as the assignment age. So this is how we will be drawing one particular graph. So let us see one example for this. Now observe this particular graph. So what you see here, see in this system, 3 processes are there, P1, P2 and P3. So how is the situation? 3 processes are there. Here I will write down P1, P2 and P3, isn't it? Means 3 instances of process are there. Then how many instances of resources are there in this diagram? 1, 2, 3 and 4. So 4 instances of this resources are. Now within each resource, how many instances are there? See, R1 is having only 1 instance. R2 is having 2 instances represented by this 2 dots. R3 is having only 1 instance and R4 is having 3 instances of that particular resource. So let us now identify which are the request stage, which are the allocation or assignment stage. Now this P1 is requesting resource R1. So this particular age is the request stage. Now R2 is allocated to process P1. So this is known as the assignment age. Now this R2 is also allocated to process P2. So this is again a assignment age. Then R1 is being allocated to process P2. So again this is a assignment age. Now this P2 desires resource R3. So this is a request stage. This resource R3 is being held by the process P3. So this is nothing but the assignment age. So this is how the resource allocation graph is drawn. Now you may be thinking that why we are actually drawing this type of graph. We are drawing this type of graph to understand whether in a particular system there is a deadlock or not. Means from drawing this particular graph, we can identify whether in a particular system there may be deadlock or not. Now, if you observe this situation, let us try to understand whether in this situation deadlock will happen or not. So what is happening here is that P1 is requesting R1 and it is already having R2. Now here P2 is having resource R1 and R2 and it is requesting R3. Now here P3 is holding this particular resource R3. So what will happen? Now this P3 is not desiring anything, right? So what will happen after some time? this P3 will release this resource R3, because we have just seen on the earlier slide, a process will first acquire a resource, means request a resource, then it will use the resource, and finally it will release the resource. So this P3, after holding this resource, since it does not desire any more resources, after its use of this resource, it will release it. So after releasing this resource R3, this P2 request will be granted, means P2 will get this resource R3. Now currently what is happening is that it is holding R1, it is holding R2, it was desiring R3. Now since P3 has released R3, so this P2 will get this R3, isn't it? So P2 will then complete its execution, isn't it? Then what will happen? It will release this resource R3. It will release this resource R1. It will also release it resource R2. Yes, after using it, it will release it, isn't it? Now, once the P2 has released this R1, so who was desiring this resource R1? P1. So P1, what will happen is that it will, once it gets the resource R1, it will use it, and then what will happen? It will execute it. So in this situation, means the all these three processes are not blocked. All will get the resources. So in this situation, no deadlock will occur. Means just looking at this graph, I could say that in this diagram, there is no deadlock. Now let us try to change this diagram a little bit and see whether in that situation any particular deadlock will occur or not. So let us change this particular diagram. Now observe here. So what I have done here is that this was assigned H. Now P3 is requiring the resource R2. Now if you compare this diagram and this diagram, first thing that you observe is that here cycle is occurring. Here one cycle is there, here two cycle is there. Now let us try to execute this situation. So here what is happening is that again P2 is holding this resource R2. It is requesting this resource R1. This R1 is being held by this particular resource P2, and it is also holding a resource called as R2. It is requiring a resource. It is holding a particular resource. This is there. Then P2 is requesting a resource R3. So here if you observe this diagram, two cycles are there, cycle 1 and cycle 2. So here what is happening is that this P1 is requesting resource R1 and it is holding a resource called as R2. Now this P2 next is holding a resource R1 and R2, and it wants resource R3, which is held by the process P3, and it is P3 is requesting a resource called as R2. Now in this situation what will happen? See, there are only two instances of resource R2. Now since there are no more resources instances, this P3 request will not be granted. Now this P3 is requesting resource R2. Since instance is not available, what will happen? P3 will go into waiting state. And what is happening? P3 will keep on waiting. P1 will go on waiting for resource R1. P2 will go on waiting for resource R3. Means what is happening? The waiting state is not getting changed in this situation. And we have just discussed the definition of deadlock, that if a process requires a resource, if it gets it, then okay. But if it does not get it, then it gets into waiting state, isn't it? And if the waiting state becomes infinite, means it will go on waiting without any result, means what? It will get blocked. So in this situation, P1, P2, P3 are blocked, isn't it? Because situation is not moving ahead. So what will happen? This diagram shows a deadlock. So from observing a particular resource allocation graph, we could say whether in a system there is a deadlock or no deadlock. So this is the use of resource allocation graph. From this graph, we can identify whether the processes are blocked or they are not blocked. Now, from this diagram, what we could conclude is that if a graph contains no cycle, then there will not be any deadlock. If a graph contains a cycle, then what will happen? Maybe the system may go into deadlock or may not go into deadlock. Means if there is only one instance of that particular resource, then chances of deadlock will occur. If multiple instances are there, then there also may be possibility of deadlock.